Bank filtration groundwater sources, such as this one shown here, are commonly found in practice. The reasons are low transportation costs, because they are found where the consumers are, and satisfactory and stable water quality. In the picture you can see Belgrade water source, which consists of 99 wells with horizontal drains, which are mostly dotted along the left bank of River Sava. These wells are immediately by the river, and their drains are, well, most of their drains are going under the river, like here. And in spite of this, even though the river is full of pollutants, the water quality is not jeopardized. So we have built a model in order to explain this phenomenon. Belgrade's water source consists of alluvial sediments dominated by sand and with one or more low permeable interlayers composed mainly of dust and clay in most of the part of the source. These interlayers have high sorption capacity. Now, in order to, here is a kind of slide that we all like to see. In order to model this type of problem, one has to solve two partial differential equations. The first one is Richard's equation, which is obtained when Darcy law for unsaturated flow is substituted into the mass conservation equation, or continuity equation. Here, the theta is porosity times sorption. Porosity time saturation. U is the Darcy velocity. Kr is the relative conductivity. K capital is the conductivity tensor in the saturated case. H is the hydraulic head. Psi is pressure head, so hydraulic head minus the vertical coordinate. And we also need equation for the concentration, so a mass transport equation. Here we have a mass transport equation for the concentration of the pollutant in the water. And since we are also considering sorption and degradation in the solid as well as in the water, then we also need another equation for concentration in the solid. So C is the concentration in the water. D is an anisotropic tensor, which what I didn't tell you and I should have is that K can also be anisotropic and discontinuous. This creates quite some problems when solving numerically. Anyway, D is an anisotropic tensor, which is modeling the dispersion and the diffusion together. It depends on this Darcy velocity here. And QC is the source term. Epsilon is the porosity. A is the speed of sorption, while B is the sorption capacity. C wedge is the concentration in the porous medium. T1/2 is the half-life of the pollutant in the water. T1/2 wedge is the half-life of the pollutant in the solid. Of course, if this is some radioactive degradation, then these half-lives are going to be the same, but in general it doesn't have to be so. So as you can see, there are many variables. And the relative conductivity, just like the saturation, are computed using the Franke-Nuchten model from the pressure head. So, if we want to consider balance, not the balance, but equilibrium case between the concentration in the water and the concentration in the solid. This means assuming that the speed of sorption is so high that it is higher than other processes and that we are considering, which practically means assuming that this A here, the velocity of exchange, is infinite. So if you take that this A is infinite, we will get that this term in brackets must be 0, and this is how we relate the concentration in the porous medium to the concentration in the water. And then we just add these two equations. We first multiply the second one with the one minus the porosity, and we get a single equation for the concentration in the porous medium. So we need to solve the first equation and the last equation to simulate this transport. And to solve it, we use our own in-house solver, which we have built, and we call it well outline and design aid. We call it like this because the acronym is then VODA, and this means water in Serbian. And we actually do a research on finite volume discretizations. We mostly concentrate on discretizations of the diffusion term, second order terms in an anisotropic discontinuous environment. We make some nonlinear discretizations of this term. This is also being done in several other scientific groups abroad. And we have built some state-of-the-art finite volume nonlinear discretizations into our code, which let us achieve properties such as finite volumes let us, as such, let us achieve local mass conservation, but these advanced discretization methods let us achieve positivity preservation and other nice things. We are currently working on the method which would be second order accurate and respect the maximum principle at the same time. This all works on three-dimensional unstructured grids. We mostly use prismatic grids, but we can actually handle just any kind of polyhedron. Even very distorted grids, it all works very fine. Our code can interact with open source software such as Gmesh or ParaView, and there is also a specialized graphical user interface which was built for our institute called Lisa, which is used for pre and post processing, and this graphical user interface is specialized for designing wells with horizontal drains. So we have built the model that I was telling you about, and these are the results that we have obtained. And here you can see the streamlines, and streamlines are telling us that the water spreads, it has to spread quite a bit in order to pass this low permeable aquifer, the low permeable layer here. So we have two effects here. One is that the water has to travel a lot because it's going all around. Maybe it will find some hole in the low permeable aquifer, or maybe it will just spread and get through the low permeable layer. And another effect is absorption, because this dust and clay in the low permeable layer sorbs the pollutant, and then there is more time for the degradation, if there is degradation, or we can say that we haven't reached the stationary state yet, because the sorption actually slows down the whole process by 1 or 2 orders of magnitude, and the micropollutants were not always there, so they're here for the last half a century. Maybe we didn't reach the stationary state yet, which means that this problem is yet to come. So, to conclude, after passing the low permeable aquifer, the color is the concentration of the pollutant. You can see that it is high concentration in the river, and then when it passes through the low permeable layer, sorry, I'm repeating aquifer, I mean low permeable layer, the concentration is much lower, and this is why Belgrade wells have a considerably higher quality of water in comparison to some other water sources where the water movement is mainly horizontal. Thank you.